known. We do not know what 95% of the universe is made of, and in a sense, you know, that's it's a shocking admission, really. Now, what do I mean by that? Well, it turns out that we sort of know in general terms what the universe is made of. We've given it titles, one of which is dark matter, but we just have no idea what the dark matter actually is. And over the last 18 years, even this story has been a bit of a roller coaster. One of the things was that if we'd had this conversation 12 years ago, right, I would have said that it was a known, if you like, that well, we reckoned we knew what the mass of the universe was. We hadn't measured it terribly accurately at that point, but we thought we knew what it was, and that's simply this rather interesting effect in general relativity, which is, you know, the Einstein theory of gravity. And what it says is that as you put matter into space, space warps. So what's interesting is if you take space with no matter in it at all, it actually unwarps and sort of goes negative. It's often known as a saddle sort of geometry. It's sort of negative, you know, uncurved, or curves away from it. So as you put matter into it, and I'm sort of doing a two-dimensional representation, it kind of goes flat, and then the more matter you put into it closes up. And we reckoned that the universe we were in was probably just about flat. And if that was the case, we knew exactly how much matter should be in it. Now, we actually managed to measure, you know, in the last 10 years, the flatness of the universe rather precisely, and it turns out our prejudices were right. The universe is indeed geometrically, you know, space is flat. It means that Euclidean, you know, the angle of the triangle, angles of triangle add up to 180 degrees actually works on all size scales. But what we also believed was that that flatness, if you like, was achieved by literally putting matter into the into the universe, and just matter. Now, what we've realized is that actually no, the universe only really wants about a third, or, you know, 0.3 of its total composition, and this symbol omega is this one we use for measuring composition of the universe, where 1 is the total composition, and then we break it down into pieces. So 0.3, it turns out that when we take all the astronomical measurements we have to date, the theory that best fits all the data is one in which matter is not 1, but it's in fact 0.3, and that's something you know, we learned really just over the last 10, 12 years. So we have a number of sort of problems to explain here. The first is that the conventional matter that you and I are made of, we call it baryonic matter. Baryon is a sort of Greek for heavy, but it's really getting at the protons that are inside us, the protons and the neutrons. You know, it turns out that that kind of material can only be about 4.5%, and I've shown it here. Or that you know, conventional material is just in this sort of luminous of this pie chart. It's about 4.5%. Now, what's even more extraordinary is when you count up all the stars in the entire universe, they are less than 0.5% of all the matter in the universe. So the first thing we realize, the first dark matter problem we have, is that there is a lot of dark, but it's conventional matter, because we know that 4.5% of the universe is made of conventional matter. I'll show you in a minute how we get that 4.5% so well. So there is what we call a baryonic dark matter problem. Now, how we actually solve that is you just say, there is gas, if you like. For gas, what we really mean is terribly diffuse sort of clouds of hydrogen, really. And these things are, this is about sort of 4%, so that makes up the 4.5% of the conventional material. But what we then have to do, the second, so that's not the dark matter problem I'm talking about, that's because we really have that just about solved now. I'm interested in this dark sector here, which we call dark matter. This is material that gravitationally interacts like conventional matter, but it has no interaction apparently with light. So most of our traditional astronomical techniques just aren't going to work. We have to, for the most part, well, for the complete part at the moment, we have to infer its presence just by the fact that it alters the way that the things we can see are moving gravitationally. And I'll give you an example of that in a minute. So this plus this makes about 27%, call it 0.3. What's the other 0.7? We know even less about that, so we just called it dark energy. Now, this is extraordinary. I mean, honestly, it is, you know, I mean, it's what makes cosmology, frankly, so damned exciting right at the moment, is that you have a lot to work with. You know, the majority, the 95% of the universe you don't know. But this dark energy, what's the distinction between dark matter and dark energy? Well, dark matter is there holding things together on the sort of galactic scales, on the galactic cluster scales. On the truly enormous, on the scale of the universe, it turns out the universe is doing a bit of a shimmy right now. We always thought, and as I say, 10, 12 years ago, I would have stood up and really sworn that this was correct. The universe underwent a big bang 14 billion years ago. And it had just enough matter in it so that after this explosion it starts slowing down, and the idea is over billions of years it slows down, slows down, slows down, and after say 100 billion years or something like that it kind of gets to the point where it really isn't expanding anymore. It's been slowing down all that time, and maybe it's just enough matter, it tips over and it starts contracting again and goes back. And that's what, when you talk about a universe that has omega matter of 1, i.e. it's completely matter dominated, that attractive force that matter experiences would be just balance the initial explosion, the initial kinetic energy. That was a really nice model. You know, it was very reasonable to believe that was true. But no, when we turn our telescopes out right now and do so on sort of length scales that are at the you know, sort of megaparsecs, you know, long distance, you know, large cosmological distances, redshifts of 1. What are we seeing? Apparently, the universe is doing this. It exploded, yes, it is expanding rapidly, it's slowing down. And then it gets about halfway through, so into sort of 7 billion years or so in, and it thinks, oh, sod this, I don't want to continue slowing down, I'm actually going to re-accelerate. So for some reason today, you know, 14 billion years on, we're actually in a universe that is re-accelerating. The expansion rate is increasing, the universe is blowing itself apart, and that property of repulsion on very large scales is the thing that we attribute to dark energy.
Doesn't that imply, that acceleration implies some kind of energy input in some way?
Yes.
Okay.
And no, lovely question. And it comes from the vacuum.
Okay.
And you say, what do you mean? Vacuum means nothing. How can you get energy from vacuum? It turns out particle physics comes to our rescue. It turns out that the fact that you and I have always assumed that the vacuum really means a vacuum and a vacuum has no property, that's particle physics. No, quantum mechanics, particle physics tells us that in fact you can get something for nothing out of the vacuum. So what's fascinating is dark energy, not only is it expanding the universe and accelerating it, but every time it makes the universe a little bit bigger, it gets more energy, because the amount of dark energy in the universe is just related to the size of the universe. The bigger the universe gets, the more dark energy is. So in fact, this fraction of 73% that we measure today is getting bigger every damn day. It's getting bigger and bigger and bigger. So it's lucky I'm sort of doing my work now, because if I waited a few billion years or 10 billion years, this dark matter fraction would be really a few percent, and nobody would respect any kind of budget proposal on it. It would all be, we'd all have to put the dark energy proposals in. Now, actually, I'm going to have to skip forward a couple of slides because I realise I'm not doing such a professional job of staying on time. Although, as all my students will tell me that. That's not. But let me. So I was going to tell you why baryons are 4.5%, but I forgive me, I'm not going to, because I think. But what I want to share with you is one of the reasons why dark energy is such a good idea. Sorry, dark matter, and in fact, cold dark matter. I'll tell you what cold means in a minute. Why cold dark matter is such a very good theory, and it relates. I think many of you will have seen this before. This is a map of the measurement of the temperature, if you like, in all directions, from as observed from satellite out, orbiting. Outside the Earth's atmosphere. It's the WMAP satellite. So what's it doing? It's basically measuring in the microwave, and it's looking at the temperature. And by that